Good morning, geometry students. I hope that you are all doing well and getting ready here for our last phase of our class for the year. This is actually one of my favorite parts coming up. Yes, we did skip to chapter 11. That's part of my plan since the beginning of the year. And guess what? I have a secret. We are in the home stretch. We have this chapter and then two sections of chapter 12, and then just one more test. It will count as a test and a half because it's on a chapter and a half. But then we are out for the year. So that's really cool. So I just want to say that to encourage you to let's get at this thing. Let's be excited because we are getting to the point where we're getting real close. So we have got this thing. So let's look at this. Today's lesson's got some real good practical stuff in it. It does apply to geometric figures, but we need to get into ratios and we need to get into proportions, and that's the good stuff. So let's get going here on this. First of all, the title of this section is similar figures. Similar figures are different than congruent because they're the same size and are the same shape, but they're different sizes. We did a little bit of that earlier in the year, so let's get going on here. We need to review what a ratio is. A ratio compares two numbers by division. You can show that as a fraction, or you can show that in ratio form with the two dots here, or in the words A to B. It's comparing A and B. Just like a fraction, even if it's written in this form, it can be reduced. So some of you will want to think of this as 10 over 6. Okay, both of them are divisible by 2, so that would reduce to 5/3, which in ratio form looks like this, 5 over 3. 8/32 is 8 over 32, both divisible by 8, reduces to 1/4 or 1:4, 1:4 ratio. 20:2 ratio reduces to a 10:1 ratio. So think about them as being fractions, and that's your easiest way to reduce. All right, lots of words on the next screen, so don't get freaked out by that. You can pause if you want to copy them down, but you do not have to copy every word, all right? I'm just going to talk about them for a little bit. Okay, scale factor, okay, is a ratio, okay, a fraction that's comparing a model and a real item. Okay, models are important for studying something that is very small and you want to make it bigger so that you can look at it more easily. For example, physicians often have models of eyes and ears and all of those type of things in their offices that you can see. And if it's to scale, that means it is exactly proportional, so that's important. When we look at a globe, we're looking at a scale or almost scale model of the Earth, which can help us to study that a lot more than if we have the whole thing. So the scale factor is going to tell you what that ratio is so that you can figure out how big the real one would be. Okay, so here's an example. The human eye is about 24 millimeters in diameter. You know what a diameter is, so we're going to think about that number, 24 millimeters in diameter. Okay, the model is 20 centimeters in diameter. So it's a diameter to diameter because you have a small one that's a model, and you have the small one that's real, and then you've got the big one that's the model, so you could study it just a little bit. So we want to compare, to find our scale factor, the real amount to the model amount. So let's take a look at that. I want to try to not have you see all of it all at once. Okay, so first of all, in our comparison, we're comparing the model to the actual, okay? The model compared to the actual. Our model is 20 centimeters, where the actual is 24 millimeters. Notice that the units are different. But in order for us to do that, we need to think about, well, 20 centimeters, how many millimeters is that? Because the actual is in millimeters. I want to compare millimeters to millimeters when you're trying to find out my scale factor. Okay, so Since there are 10 millimeters in a centimeter, and we went over that before, that means that 20 centimeters equals 200 millimeters. And if you need to go back and review that in your notes, then please do. Okay, so the next part is that if we want to write the ratio of that, we're comparing the model, which is 24. We're comparing the model, which is 200, sorry, with the actual that is 24. Okay, 24 is the smaller one in this case. Our model is smaller than in real life how big the eye is. In order to find the scale factor, what you need to do is you need to reduce this fraction. Now, this is not a fraction reducing exercise, so if you have trouble with that, you can always use a calculator to do this. There is a Texas Instruments has graciously allowed the TI-84 to be downloaded. It would work the same way. If you check, there's a link on the bottom of the of this page that you clicked to find this, and you could click on the links and download that for your PC if you have nothing that you can do, and then use your math fraction button to reduce. Okay, 25 to 3 is our scale factor. 25 millimeters in the model is the same as every 3 millimeters in the actual amount. Okay, so our scale factor for our model, we could write it as 25 to 3, like this with the 2 dots, or you could write it as a fraction, 25 over 3. And when you enter it in the quiz or test, you can do it either way. That's just fine with me. All right? What it tells us is what I just said a second ago. For every 25 millimeters on the model, there are 3 millimeters in the real eye, and that can be very, very helpful, especially to those who are needing to study about the eye. Okay? All right, so a proportion shows 2 equal ratios. This is where it can be useful. In that model of the eye, you might want to know, well, how big is the pupil, and be able to compare that with the pupil on the picture, or how much does the pupil expand, or how, various different pieces of the eye. So the proportion allows you to compare them and use the idea of equal ratios, because every piece in the model is the same ratio as the piece in real life. It's the same ratio. So the proportion shows 2 equal ratios. It's just like reducing fractions. 6/10 is the same as 3/5. This is a different way of writing it. 6 is to 10 as 3 is to 5. That's how you would read that. These double set of dots is like an equal sign. These dots are like the fraction bars. If I have this and I have it written in fraction form, I prefer fraction form. We're way much more used to it. So I'm going to be working almost exclusively in fraction form, except for to explain a couple of concepts. Okay, so we would say A is to B as C is to D. So it's saying these are the 2 parts that go together, just like these 2 parts go together. And it is important, it's important that you're careful how you arrange them, and I'll talk about that shortly. Okay? You might remember from your algebra class the cross product property, that if you have things like this, you can solve it using cross products. Very, very nice trick. You should have learned that before, but if not, we're going to go over it here almost as if you hadn't learned it. A times D equals C times B. Okay, the way that is expressed in the most correct way is that the product of the means equals the product of the extremes. The product of the means equals the product of the extremes. You would hear that term. The word means and extremes come from, if you write this out in your format like this, extremes, think about them as being at the extreme ends and the means being in the middle. Now this is not a mean like an average, it's called a geometric mean. That lesson is way down the road here, but before we get to the end of your geometry. So for right now, just throwing out these words so that you have heard them. Not necessarily going to be on a quiz or test. It just makes it's good if you can speak the correct math language. Product of the means equals the product of the extremes. In your practical terms, it means cross multiplying works. And let's do some examples of how it works. Or actually, let's do why it works first of all. We know we were doing proofs, so this is a proof. But you don't have to be able to do the proof. Just follow along. Don't skip past this. Just listen for a minute, okay? All right, so first of all, if I multiply both sides by b, I can do that because of the multiplication property. When I do that, my b's will cancel out and I get something like this, simply because I'm using the rules for simplification. Then, if I want to, I can multiply both sides by d because of the multiplication property of equality. That means that's legal. So the d's will cancel out. In other words, I can simplify it. So here what we've had is we had this beginning turned into this end, and that's the end of the proof. We have this, and we're trying to prove that we can do cross multiplication. So that's done. We proved it. Yay. Now let's use it. Using it is what you're more interested in, so let's move on with that. If I'm talking too fast, hit the slow down button. You know how to do that. All right, so cross products have to be equal as long as we have an equal sign in here. So here's where we need to be a little careful. That means that x times 6 equals 5 times 9. I like to think of it as just kind of swooping through. X times 6 equals 5 times 9. 5 times 9 is 45. That's where that came from. X times 6 equals 5 times 9. And then you have a problem that you're very easy to solve. You can divide both sides by 6. We get 45/6 that way, which can reduce, both are divisible by 3, to 15/2. So x is 7.5, or 7.5. You could leave it in your decimal form or your fraction form. You can use any calculator you choose on something like that. I'll choose the other calculator because it's an easier calculator, and this shows up anywhere, just a plain old calculator. So you're taking 45 divided by 6. And you get 7.5, and you can be done with it there. Okay? That's great for any time there's just single things. Notice here the variables in the denominator. That can happen sometimes. So we're going this way and this way. 4 times 21, 84, equals 3.5c. Divide both sides by 3.5. And we get 24. Once again, you can use any simple calculator for that. You know, taking 84 divided by 3.5. 84 divided by 3.5. And you get 24, nice and simple. This one, be careful when you have something like that. Be careful when you have a sum or a difference in one of your locations. You're still cross multiplying. So we're taking 5a times 14, which would give you 70a. This one, be careful. This goes this way. 6 times the whole thing times parentheses a plus 2. So this way gives you this one. This way gives you this one. Then don't forget that when you have a number times a sum, you have to distribute. This is taking you back to your algebra days. 6a plus 12. You've got a variable on both sides. Back to your Algebra 1 days. Take away the 6a from both sides. Then you divide both sides by 64. Don't divide both sides by 12. Divide by whatever's multiplied times the a. And then once you've divided both sides by 64, you reduce the fraction. Both are divisible by 4. So if you were doing it out the long way, you would have 12 divided by 64. This calculator does, I don't think it has a fraction button. Nope. Not seeing a fraction button. It might be hiding in there somewhere. Nope, not seeing it. So you really do need to find, if you're not good with fractions, you need to find a way. If you're good with fractions, then really honestly you don't need this calculator anyway. But if you do need it, 12 divided by 64, there's your answer, and you want to make it into a fraction. 3/16. All right. So what's that useful for? Is useful for solving anything where you end up having a proportion as your answer. Now, there are some other properties. Because cross multiplication works, even if both of these fractions were turned over, okay, as long as it's both of them, we still have something that produces equal values. In other words, b over a equals d over c. We still have b times c equals a times d, same thing. The means can switch. Remember, c and b were the means. So that's fine. It's called the interchange means theorem, but I'm just trying to make it simpler for you. These two can switch because when you cross multiply, you're getting the same thing. And the extremes can switch. Okay? D and A can switch locations. That's fine because these two still works. What can't happen is you can't flip over one side and not flip over the other side. Because if I flip this over to b over a, then instead of having b times c, I'd have b times d, and that would be a whole different problem. So it does matter where your numbers go. However, there are variations on the right way to set it up. You just need to be very careful, and as we go through examples, I'll point some of those things out. Okay? They all have the same cross products. You do not have to write down every word. And here we go. Similar polygons are polygons that are the exact same shape but different sizes. We already mentioned that. This symbol right here looks like the top of a congruent sign. Means is similar to. Not equal, but there are some things that are like it. And when I say they're like it, I mean that the angles are all congruent. Okay, angle for angle. When you take this one and you blow it up and turn it into this one, or this one and shrink it down into this one, the angles all stay the same. However, the sides are not the same, but they are proportional. Okay, so what does that mean? That means that angle E is congruent to B, D is congruent to A, F is congruent to C. I do want you to write this part down. A is congruent to D, B is congruent to E, C is congruent to F. So those numbers will match. When we look at the proportion, AB matches with DE, AB goes with DE. Go back to the little one. AC goes with DF, and BC goes with EF. So even though BC and EF aren't equal, you can see that BC and EF are the ones that are, their ratio equals this ratio. Okay? And AC goes with DF. And they are all equal. You probably would not use the extended proportion that includes all of them all at once. You do it as a group of two that were equal to each other, and then you could use some cross multiplication, and we will go through that process so that you have a number example. Always makes it easier with a number example. Okay, so to figure out whether they're similar or not, okay, if you want to do the long version, you have to first of all find out if all the angles are congruent, and then you need to find out if the sides are proportional. So let's tackle the angles first. On this problem, angle Q equals U, V equals S. So what that would tell you, because you know from the past that if two angles are congruent, the third angle is congruent. Some of you might remember that. That's our angle similarity theorem, or angle implies angle theorem. So this angle has to equal this angle because two angles are congruent means all three are congruent. So we've got our three angles, so we're good. Next, we need to check on our proportionality. So what we need to find out is we need to find out if QR and TU have the same ratio as QS and VU, and if that has the same ratio as SR and VT. So we have to go through piece by piece. So let's check the ratio of QR to TU. Okay, QR to TU. That equals 16/12. That's 4/3. Okay. We want to check RS compared to TV. Now, since we compared the big to the little in the first one, we have to compare the big to the little, always going back to make these fractions line up, or this check doesn't help us any. We need to check RS to TV. RS to TV equals 15/11.25. This is where you really do need your calculator. Okay. You could even use the dumb calculator if you wanted and just write down your decimals as long as you use the right thing with the repeating decimal. But if I take 15 divided by 11.25 and I enter, and I do math and fraction again, this is a really handy button, we get 4/3. Okay, then QS 18 compared to 13.5. And once again, if we plug that in, we would get 4/3 again. So these are all the same value. Because they're all the same value, the ratios are all equal. 4/3 is the scale factor. They are similar because the angles are congruent and the sides all give you the same. 4/3 is the scale factor that we talked about before. Another word that you might see in your book is the similarity ratio. So those just are thrown out there so that you can see them. Now, if we want to write down the similarity statement, okay, you need to use the similar symbol. It does not matter what order your first letters go in. Okay, QRS, I chose that, but you need to make sure that the corresponding parts line up, just like we did for congruence. So Q goes with U. The easiest thing is to look at the congruent places. R goes with T. R is in the same spot as T, and S is in the same spot in the triangle as V. Look at your congruent markings, and that will help you with that. Okay, now, this is one type of thing you can do. You can find out if they are similar, but most of the time you'll be given something that's similar and then have to find missing pieces. So you'll have one figure, you'll have another figure. Okay, when you're doing these, if you have one part that is the same piece in two of the figures that both have numbers, that's the thing you need to start with. Okay, 12 goes with 21. So 12 goes with 21. So my similarity ratio, since I've been given that these are similar, the proportions always have to match up. 12 goes with 21, so I reduce that, and in this particular case I've gone from the small one to the large one, or you could say I went from the left one to the right one. So for every one of these others that we're trying to find, X, Y, Z, and U, you're going from the small figure to the large figure is going to be in a ratio of 4 to 7. So 4 to 7. If I want to find X, I need to find the corresponding piece in the small one. So 4 over 7 equals 14 over x. It equals 14 over x because our ratio is the small figure to the large figure, the left figure to the right figure. So I have to do small to large here also. Once you've done that, it's a matter of cross multiply. 4x equals 98. Divide both sides by 4, and you get 24.5 on that one. Small to large, let's think about y. Okay, here's this piece on this figure, goes with this piece on this figure. 4 goes with 7, small goes with large. 4 goes with 7, like 26 goes with y. Cross multiply. So we get 4y equals 182. Then divide by 4. We have our answer. Let's think about z. 10 and z are the ones in the same place. 10 goes with z like 4 goes with 7. 4 goes with 7 like 10 goes with z. Cross multiply. 4z equals 70. Divide. 4 goes with 7. 4 goes with 7. Last one, like 16 goes with u. Cross multiply. Okay. Now I do not want you to be deceived into thinking that you always have. I don't want you to be deceived into thinking that you always have the variable in the denominator. So I want to throw in one additional example. Let's see how this works. If I all of a sudden know these things are proportional, let's draw in another line really quick. Okay, let's say I have this one goes from here to here, this one goes from here to here. And since they're proportional, those are meant to be the same piece. Let's say I have, let's put a C over here. And let's say that this length, let's see, Z was 17.5, U was 28. So let's say that this one is 20. Okay, so this would have to be given to you as well. Our scale factor is still small to large is 4 to 7. But in this case, small to large, C is on the small side, and the large side is 20. Okay, cross multiply, we get 80 equals 7C. And we would need to divide both sides by 7. And honestly, this one's going to give me a decimal that doesn't end. So if we divide that out, oops, let me see here. Sorry. If we divide that out, we're going to end up with a fraction, a decimal that doesn't end. So I'm just going to go old school here. We have 7. We have 7, we have 3 left over, so 11 and 3/7 would be your answer for C. So here's the thing, you're setting up your proportions, small to large, left to right, and then each one of the subsequent ones you have to set up in the same pattern or it doesn't work. Okay, so, okay, great. So we can do shapes. That's fantastic. Well, actually, yes, it is. It is fantastic because it works for any similar figures, whether they're models, anything that can be measured. If you have a scale factor, that it just all works out. If anyone is into making actual physical models of things, the scale factor is super important on that. You want things to be proportional or they just don't look right. Another thing that it's useful for is food. And I like food, and I know a lot of you like food too. Some of you may or may not be into baking or cooking. However, you never know what you're going to end up doing at some point in your life. Some of you might decide that you want to make things for a large group. I have encountered this type of a thing in life multiple times. Even in the case of wanting to make something, one year we were making cookies for students, and I needed to figure out how much of the ingredients that I needed for a Christmas party, I believe. And so I needed to use this type of math. So this is pretty good thing to know about. So we have a recipe, and it's going to make enough cake to serve 8 people. And it calls for 1.5 cups of chocolate chips. How many cups of chips will you need if you want to make enough cake to serve 92 people? Okay, so you can make cake batter in larger and larger and larger pans, but you need to have enough batter to make the appropriate amount of cake. Anybody who gets into catering or anything like that. So we want to compare the amount of cups of chocolate chips to the amount of people. So 1.5 cups is going to give us 8 servings, or enough for 8 people. Now, I do not have to turn cups into servings. I do not have to, like we did at the beginning, we had millimeters and centimeters and they had to be in the same unit. You don't have to do that when you're using it as part of a proportion. As part of a proportion, you're not trying to get similar units. If it was part of a proportion, you could have left millimeters and centimeters separate, as long as the ending unit was going to match what your starting unit was. It's a whole different type of thing, but do be able to convert if you're asked to convert. Okay, anyway, back to this. This is important. 1.5 cups translates to 8 servings. I want to serve 92 people. That means I want 92 servings. Notice that I have the fraction set up, so if I have the number of servings in the denominator on one side, it has to be in the denominator on the other side. But I'm needing to find out how many cups of chips I'm going to need to have. All right, so we can then cross multiply. 1.5 times 92 equals 8c. Then you divide both sides by 8, and I get 17.25 cups of chocolate chips. And that's how much I would need in order to make that work out. It's just a matter of simple proportions. Like I say, the caterers and things have to use proportions all the time in order to be able to figure out how much of something they're going to need to be able to serve a certain amount of people, or even if you plan on self-catering at some point. And you may not have 92 people, but you may have your Thanksgiving dinner that you're planning, and you need to make sure that you have enough, but you don't want to be eating your leftover Thanksgiving until July. And so you want to make sure that you're at least close to being proportional. All right, so some good practical applications for that. I hope that you have a great day. Let's get going on that assignment that's due at the beginning of class tomorrow. Just like when you're in class, we have a lesson, and then you have a homework that goes with it. So I'm keeping the same pattern for you so that you can make sure that you're not overwhelmed. But do keep in mind that's what we would do in class. We would have a lesson, and then we would have a homework assignment to go with it, and that would be something you do later. So if it's becoming overwhelming, why don't you take a break between watching the video and then doing the assignment? That's just a good idea, because that's what you would do at school. You'd come to class, you would listen and pay attention, take notes, and then you would do the assignment later. So let's get you into some good habits, and understand that we're going to get there. We are in the home stretch, so just hang in there. Yes, we are in Chapter 11. Chapter 10, although it has some good stuff in it, is more than adequately covered in Algebra 2. It's a whole different branch, so I just chose to not do that. So there we go. That's it. And I wish you all the best and am praying for you. God bless.